Hey, feeling good, like I should. When in dark, I walk around the neighborhood, feeling blessed.
Alrighty, today's lesson is 2.1.4 called Using Zero. And today what we are going to do is we're going to revisit what we learned in 7th grade about adding opposites together to form zero pairs, and do that in the context of simplifying algebraic expressions. And we're going to learn how to find the zeros with our algebra tiles. So just to revisit from last year, when two numbers have a sum of zero, they're called a zero pair. And so you may recall we started off with using the integer tiles, the plus and the minus tiles, and we would have circled every time you had a zero pair, you would circle it, and they would essentially cancel each other out because they add up to zero. Now we would apply that using like this problem, 5 plus a negative 5. Let me go ahead and show 5, 1, 2, 3, 4. That is an integer representation of positive 5. And then negative 5, 1, 2, 3, 4, 5. And what do we see there? We see a 0, we see a 0, we see a 0, a 4, 0. We got all zero pairs. So when everything zeroes out, then your answer is 0, right? So when you add opposites together, you always get a sum of 0. So we call these zero pairs. Well, now that we're working with variables and algebra tiles, this particular statement is like saying, okay, let's take x and let's add it to negative x. It doesn't matter the value for x. If x is equal to 4, then this one has to be equal to negative 4, because this is always going to be the opposite of that. If this were equal to negative 7, the opposite of negative 7 would be positive 7. So negative 7 plus positive 7, that looks a little floppy, but I think you get the idea. These are all equal to 0. Okay, so these are all examples of zero pairs. And today we're going to be focusing on using the algebra tiles to find zero pairs. And once you have them as zero pairs, they can go away. And that's how you simplify these expressions. Okay, so today you will continue your work with rewriting algebraic expressions. As you work, ask yourself these focused questions. How did you see it? How can you write it? And is your expression as simplified as possible? So there are 3 little scenarios here that I want you to read. I'll read out as well. And then we're going to answer some questions at the bottom. It says, Julie babysits for her neighbor's baby and stuffs the $15 she earned into her purse. When she gets home, the $15 is nowhere to be found. It must have fallen out of her purse. The Burton Pumas football team completes a pass and gains 12 yards. But on the very next play, the quarterback holds onto the ball too long and gets sacked, losing 12 yards. And Rolando's he digs a hole in the sand and places the sand he removes into a pile that's next to the hole. So you see how that pile's over there? There's the hole. He's pulling it up. Then someone comes along and decides to push that sand right back into the hole. So what do all of these situations have in common? What do they all have in common? She makes $15, but then she loses $15. They gain 12 yards, but then the next play they lose 12 yards. They dig a hole, but then they fill that hole right back up. What's happening in each one of these situations? Well, I think you kind of are getting the idea. All these situations are a net zero. Whatever was gained is taken away. So the $15 she gained from working got lost. So that is like saying $15 minus the $15 because you lost it means you're back to where you started with $0. The player gained 12 yards, but then they lost 12 yards on the next play, so they're back to where they started. They are essentially, over 2 plays, have gained 0 net yards. And then the same idea here, but in this case, we think of it as in the terms of a variable because we don't know how deep the hole was. But you're digging the sand out of the hole, so it's kind of like you're taking sand out of it, but then that same amount of sand gets put back in, and so you're at a net 0. Okay, so today we're going to be looking at some situations with just algebra tiles for now. Eventually, we may get into some word problems where there are some 0 pairs to be found somewhere within the problem, but let's not worry about problem solving yet. Let's just work on the mechanics of what we do to simplify expressions using using algebra tiles. Okay, so here's the direction for problem 35. It says, how can you represent 0 with tiles on an expression map? With your team, you're at home reading this and watching this video, so you're working on your own. Try to find at least 2 different ways to do this, or more if you can, but you know what? I mean, there are a lot of different ways. Let's just stick to 2 to keep this as simple as possible and as quick as possible. Okay, so go ahead and draw a couple of representations of expression maps. And then what you want to do, and you kind of saw it on the very first page that I did at the beginning of the video, where you saw how x and negative x, when added together, made 0. Think in those terms, and just remember, since you're doing this on your paper, when you are doing one that's shaded in, that represents a positive one, and when you leave it open, unshaded, that represents the negative one. So when you're working with X tiles, if it's shaded, it's going to be equal to X, and when it's open, it's going to be equal to the opposite of X, or negative X. I would recommend you not mess around with Y's. Let's just stick with X's, maybe X squareds if you want to do X squareds, and the unit tiles, okay? So go ahead and give that a shot, pause, and then I'll do a couple of them over here as well when we come back, okay? So take a little time and do that. All right, so I'm going to show you just a couple that I'm going to do, and obviously I can't see yours, but you should be able to look at what I'm doing and determine whether or not yours make a 0. Okay, so the obvious one, remember we had done x and negative x. Okay, that works just fine. So you could say that x plus negative x equals 0. That's an example of a 0 pair. There's another way I could do it. I could put the x on top, and I could put an x in the negative region. That is also a 0 pair, because it's kind of like we're doing the reverse of KFC here. Instead of changing that from a minus subtraction problem to an addition problem by adding the opposite, we could just do it in reverse. So we could say take x and now subtract away a positive x, and that is also going to be equal to 0. So those are 2 different ways of doing it. Now, if I wanted to use different tiles, let's say I wanted to use the x squared, I could do, maybe I'd even do this. We'll take an x squared and a 1 and add that to a negative x squared and a negative 1, and this would be a 0 pair, and this would be a 0 pair. If I chose, I could move this guy across the street, and that would be equal to 0, because this would be essentially saying x squared plus 1 minus, or plus 1 plus a negative 1, that's a 0 pair, minus x squared is going to give you 0. So let me go ahead and show. First one we had was x squared plus a negative x squared plus 1 plus a negative 1, right? Here's a 0 pair, here's a 0 pair, it's equal to 0. And in this part, it's just me taking the x squared minus an x squared, that's this, they cancel each other out, and then the positive 1 plus a negative 1. And if I wanted to take this guy and move it across the street, I could do that, and this guy becomes x squared plus 1 minus x squared minus 1, or another way of saying that would be x squared plus 1 minus x squared plus 1. If I put this in parentheses, this entire quantity being subtracted from that, they're the same thing, so they're going to equal 0. So hopefully what you're seeing from this exercise is where and how you locate 0 pairs. So I want you to copy this down. 0 pairs on an expression map, okay? When you have opposite tiles in the same region, they form a zero pair. Okay, so opposite tiles in the same region form a zero pair. That's like when we had this guy up here. These are opposites in the same region, okay? If I move this guy down here and I change that to its opposite, these are opposites in the same region. It doesn't matter if the region is the positive region or the negative region. If you have opposites in the same region, they form a zero pair and cancel out. So this would go away, this would go away, and now we have nothing there. So we have 0. If you have the same tiles in opposite regions, that would form a zero pair. So the same tiles in the opposite region form a zero pair. So here we go. You got the same tile in opposite regions. X squared minus x squared is equal to 0. X minus x is equal to 0. If you take 1, take away 1. Okay, so this is a zero pair. These guys would cancel each other out. These make a zero pair. They would cancel each other out, and these make a zero pair. They cancel each other out, and you're left with nothing. Okay, so go ahead and pause this and write that down. That's really important to understand. And when you're ready, unpause, and then we'll continue. So problem 36, Gretchen used 7 algebra tiles to build the expression below. Your task is to, and you can use the online, oops, is that the, hold on for a second. Okay, so in the online book, you see problem number 36, it's got everything. You can use the student, whatever you call it, the student tool, the e-tool, and this has it set up exactly how it's set up here. And your task is to find 3 different ways, and you should use different numbers of tiles every single time. So essentially what you're going to be doing is look for 0 pairs and remove the 0 pairs. Okay, so if you want to draw the picture, there's a couple different ways. I'll show you how to do it with just the drawing, but if you like manipulating this e-tool, go ahead and do that as well. Okay, I'm going to continue using this. And I'm going to go on to the next page. Okay, so go ahead and see if you can come up with 3 different ways. Now I'll show you the original way. Just go ahead and write this out. This is 2x's plus negative x plus 1. X's plus negative x plus 1. All these are being added together. And then in the negative region, these are being subtracted away, and it's only the 3 1s. So it's minus 3. Okay, so that would be the original way to write it. I want you to identify 0 pairs and remove a 0 pair and then rewrite the expression, and then remove another 0 pair and rewrite it again, and keep doing that until you get a simplified expression where you cannot find any more 0 pairs. Okay, go ahead and take some time with that. All right, let's see what we got here. So the first 0 pair that I saw was these 2 guys, opposites in the same region. So if I remove those 2, it's like me taking your one of those x's, 2x plus a negative x is equal to 1x, and now we still have the 1x here plus the 1, and then still the minus 3. So what else can we do here? Well, here's a 0 pair because these are the same tiles in opposite regions. So I'm going to get rid of those, and that leaves me with x minus 2. And if I wanted to, I could move these guys across the street and change it to x plus a negative 2, but it's not necessary to do that. You can just leave it like this. So x minus 2 is the simplified version of this expression. So basically what we did is we combined like terms with the x's. 2x plus a negative x is 1x, and eventually with 1 minus 3 gives us that negative 2 for a final answer of x minus 2. Okay, now you're going to take some time on this. You're going to build each one of these expressions, and it says to do it 4 different ways because they think you're working, CPM thinks you're working in a team with 4 people. I actually might suggest that you just do it one way. For sure, get one way. If you can come up with two different valid representations, that would be wonderful. Um, and I'll model doing two different ones. But as long as you can come up with one, that would be good. But actually, no, you should do two because I think, well, maybe you can, maybe you can't. I think two of them, one of them can be simplified, but two of them probably can't. Okay, so go ahead and copy these three down. And once again, you've got access to your e-tool. In this case, do we have one for problem 37? You'd probably have to use this one again. And you could just clear these guys out by highlighting them and then hitting the delete button. And then you can build each one of these and then start playing back and forth with them, okay? So you go ahead and work on that. And you know, I know that if you're choosing to use the online tool, you still should be putting it into your journal. Because if you're not doing this work in your journal, you're just writing answers, I don't know that you're going to understand when you go back and prepare for the test what you were doing. So take the time. In these first few lessons, we're doing more drawing, but you're going to stop doing that pretty soon, okay? Just bear with me while we're doing this fundamental exercise. Follow the directions and do these sketches. It'll pay off in the long run. It'll help you understand this much better. Okay, so let's start with negative 3x plus 5 plus y. This is one way to represent this, okay? Now, I'm looking here. I don't see any zero pairs. I don't see, there's nothing down here. So we're going to have to look for opposites in the same region, and we don't have any opposites in the same region. So for me to rewrite this, I'm just going to kind of rearrange things. Like, for instance, I might take these three x's and move them across and change them to look like this. And now, essentially, what I've done is I've rewritten the expression as 5 plus y minus 3x. So I'm just kind of using commutative property here, moving this term around. But I'm not really able to simplify this expression anymore. So this is two different ways that you could write that expression, but it's already in simplest form. It's just a matter of rearranging the terms. This is how the opposite of 2y plus 1 would look, right? They're in the negative region or the opposite region, and you got two negative y's and a positive 1. Now, how could I rewrite this guy? Well, if I considered doing distributive property here, I would change this guy to its opposite, which means I would move the negative 2y's across the street, and then they become positive 2y's. And then I would also change this to its opposite, which means this guy would move across the street, and it would change to its opposite when it moved across the street and become negative 1. So then this becomes 2y plus a negative 1. But at the same time, you didn't necessarily need to move this guy across the street. If you'd wanted to, you could have kept him there. Oh, you did. Is that it? Yes. You could have kept him there and written this as 2y minus 1. That would have worked as well. So here I've got three different representations of this particular expression, but nothing canceled out. So you're not really simplifying it. You're just rewriting it in three different ways. And now 2x, here's two x's. In the minus region, you're taking away an x and 4 negatives, or a minus 4. So if I did the same thing that I did before, I could send in the dive bombers and change this to, this moves across the street, right? That becomes a negative x. But actually, I'm not going to do that yet. I found a zero pair here. This is the first one of these expressions where you've got a zero pair. You've got the same tile in opposite regions. They can actually cancel out here, and you end up with x minus a negative 4. But to be honest with you, I sort of like the idea. I think this is really helpful for students. If you use the distributive property here, that is pretty much the same thing as moving these guys across the street and changing them to their opposites. So the x is going to change to a negative x, and the 4 negative ones would change to 4 positive ones. So watch how this happens. 2x, take the opposite of x, so that's negative x or plus a negative x, and take the opposite of negative 4, which becomes positive 4. And now you see your zero pair there? They're together in the same region, but they're opposites in the same region. So by choosing to remove the zero pairs after I'd used distributive property, it sort of makes more sense for the order in which we would solve this problem without the tiles. So I want this to make sense in the order that we would normally solve these, because you're not going to be drawing tile figures forever. So this actually becomes x plus 4. So once again, 3 different ways that we can write that expression, and this is the simplest form version of that expression. All right, so what I'd now like for you to do is copy these 2 expression mats down and write the original expression down. Now, I will help you with writing the original expression down, okay? We're going to start, you've got, well, first of all, pause and draw these into your journal. Then unpause, and I'm going to continue talking, and you'll just pick up with me talking, okay? Okay, so you've just paused and spent a good time writing this in, and now you're ready for me to show you. When I'm writing down these expressions exactly as they're shown, I'm going to start in the positive region. Everything up here is being added together. So I start with all my positives. I got a positive x being added to 2 negative x's that are being added to negative 1. So x plus a negative 2x plus a negative 2 are all in the upper region. And this down here, that's our subtraction. We're subtracting away 2 negatives. Now, while you're solving this problem, hold on for a second. I have that. No, I didn't. Okay, good. What you can do here now is you can do something. You can strike out your zero pairs. So you recognize that this and this cancel each other out because they're a zero pair. That's the x and one of these negative x's, leaving you with just a negative x. And then you notice how you got negative 2 minus a negative 2, which when we do KFC becomes plus a positive 2. Well, that's because these guys are the same tile in opposite regions, and they will cancel each other out. So eventually what happens here is you eventually end up with that negative x gets added to 0, because this zeroes out, right? Negative 2 plus 2, and one of those x's gets canceled out with a negative x, leaving you with just that negative x. So we end up with negative x, okay? Now on this one, let me go ahead and show you striking everything out. There's a zero pair, there's a zero pair, there is a zero pair, and you're left with 1 minus x minus a negative 1. But you might consider moving this guy across the street and having that become another positive 1, right? Remember when you move things across the street? So I think our final answer is going to be 2 minus x, or if we move that guy across the street, negative x plus 2. Okay, so I'm going to go ahead and uncross these out just so you can see that we started off with the expression x plus negative x plus 1 plus 2 negatives, negative 2. Those are all being added together because they're all in the upper region. And then we're going to take away an x, and we're going to take away negative 3. So after doing a little bit of zero pairs here and a little bit of KFC there, we change this. They cancel each other out because they form a zero pair. 1 plus a negative 2 gives you negative 1, and then the negative x and the positive 3. So essentially that is me, if I were to do it this way, canceling out the 2 negatives, canceling this guy out, and then moving these guys all. Oh, wait, no, I guess I would cancel out. Hold on for a second. Hold on for a second. I'm not moving things across the street yet. I canceled those out, but then I also canceled this out. So now we move these guys across the street, and that becomes 2 positives. Move this guy across the street, and that becomes a negative x. And so we end up with a final answer of negative x plus 2, or I suppose it could have been 2 minus x if we had decided to leave this guy down here. For that matter, you could have had the opposite of negative 2 minus x, but that's going to get a little bit too complicated. Okay, so either one of those are acceptable ways of writing this expression in simplest form. All right, so simplify each of the following expressions, and then we will be done by building it on your expression mat and removing the zeros. Okay, so go ahead and you can use the tool. Let's see if they've got one for this problem. Is this number 39? Yes, they've got an expression mat there for you. Oh, no. No, you probably want to use the E tool again. So come up here, use the E tool from problem number 36, get rid of everything that was on there, and you can build them and make sure you draw them on your journal, in your journal, as you remove your zeros. And I'll do these here, okay? So go ahead and copy down these two expressions and then build them with the mats, draw pictures of them, and then find out where your zeros are and simplify everything from there, okay? All right, let's see how you did. Let's start with A, where you have 3 x's, here are my 3 x's, minus this quantity inside parentheses, minus the 2x plus 4, okay? So, if we want to remove zeros, we have the same, or I'm sorry, do we have different tiles in the same region? No. Do we have the same tile in different regions? And this, the answer is yes. So we are going to be able to remove those. Now, I do want to just kind of record this so you can see exactly what's happening here. I would be using the dive bombers here and calling this 3x minus 2x minus 4, okay? So that's another way of saying this. Instead of having the parentheses around these, 3x minus the 2x minus the 4. And the 3x minus the 2x is going to result in these 0 pairs going away. So now we're left with x minus 4, which is our answer in simplest form. And you could move these guys across the street and call it x plus a negative 4 if you wanted to, or just leave it how it is. But this would be the simplified version because there are no more 0 pairs. This one's a little bit trickier. I had to think about this a little bit. So remember, anything that's a positive or being added goes in the top region. So I've got my 7, 1, 2, 3, 4, 5, 6, 7. And then let's come down here for in this, we're subtracting away 4 y's and 3 negative 1's. So minus 4y minus negative 3. And then we come back up here because we're adding 2 y's, right? If it's being added, it goes in this region, unless it's being added inside parentheses, and this is telling us to put it in the lower region. That's where this gets really, really complicated, using the tiles. But I will show you the traditional way of how to solve this below, using the distributive property and going from there. And then, of course, there's your minus 4, right? So it seems like it would be easier to write it this way. Let's put these two terms together, 7 plus 2y, right? Use commutative property. And then we're going to take away the 4y's and also take away the negative 3 before completely subtracting away the 4. Now, do we see any 0 pairs here? Did I see some 0 pairs? I see that we've got, what do we have here? We've got some zeros down here that we could get away or take away. So those would go away. So it's kind of like adding these guys together, right? Because that's going to be a positive 3 plus a negative 4 gives you the negative 1 there. And then we could have taken away 2 of these guys and 2 of these guys because they're the same tiles in opposite regions. So that's like combining these two, and now you're left with minus 2y's. And then you still got this 7 there, right? Up on the top. So we've got one more 0 pair. We've got the one on the top and the one on the bottom. when those go away, you end up with 7 minus the 1 gives you 6 minus the 2y's. Now, do you want to move these guys across the street? Because you can. You would just change that to 6 plus a negative 2y's. That would be fine too. They both mean the exact same thing. But this is probably the easiest way to write your simplified expression, which started off like this. Okay? So eventually, we are just going to go through a certain process, use distributive property, use commutative property to rearrange the terms so you can get the like terms together. Sometimes you're adding positives together. Sometimes you're adding positive to negative, which means you're going to find 0 pairs and you're going to cancel those out through subtraction. And eventually, you rewrite your algebraic expression so every term is its own unique term. You cannot combine any more like terms. So you got a constant term and a variable term, a y term. They cannot be combined because they are not the same thing. We don't know what y is, so we can't evaluate this expression until we know that. Okay? So keep working hard on this. Oh, it was over 30 minutes. Sorry, but there's a lot going on in this lesson. So once again, show your work, make your corrections, your best, and this will all start to make sense. This will all just be second nature to you pretty soon. All right, take care. Good luck on the homework. Bye.
Hey, feeling good.